That gray, durable material, cement, is actually the silent backbone that holds up luxury buildings and billion-dollar streets around the world. Once, they were nameless rocks sleeping beneath the earth. They were awakened by explosives and steel gears, then subjected to a ruthless ritual. They were burned in scorching heat, crushed under high pressure, and transformed into the material that holds the world together through technology. In this video, we will explore the extraordinary transformation of a material that seems familiar, but whose story is far from simple. Cement. Quietly, it has built structures worth trillions of dollars worldwide. However, few people would guess that the seemingly simple ash left behind by volcanic eruptions forms the foundation of humanity's most durable building material. Around the year 128 AD, the Romans developed a type of concrete using these ashes that could withstand centuries of use. Evidence of this can be seen in structures like the Pantheon and the Colosseum, which still stand tall in the heart of Rome. However, this material that once supported the grandeur of empires has become a silent burden for the modern world. The cement industry emits over 4 billion tons of CO2 annually. This accounts for approximately 7.5% of global emissions, surpassing the combined total of the aviation and shipping industries. Thus, the material that enables us to build our homes is also silently contributing to the planet's warming. Behind every bag of cement lies a process that is much more complex than we imagine. And this is where the race for a truly sustainable future begins. The journey begins with the extraction of limestone layers from quarries near production facilities. Limestone, which makes up 75 to 80% of the mixture, is the most important raw material as a source of calcium oxide, CaO. The extraction process begins with controlled blasting. Holes are drilled at a depth of 8 to 12 meters in a predetermined grid pattern, and then emulsion explosives, or ANFO, electric detonators, and filling material are placed in these holes. After loading is complete, workers sound a horn as a warning, and the blast is carried out in accordance with strict safety protocols. As a result of the blast, the rock is systematically broken into thousands of tons of small pieces. Tracked excavators load these rocks either into 40 to 60-ton dump trucks or primary belt conveyors. Excessively large rocks are broken on-site using hydraulic breakers. The rocks are then sent to the primary crushing station, which is equipped with jaw or hammer crushers and reduces the rocks to pieces smaller than 100 millimeters. The next component is clay, the second most important material in the mixture. It is extracted from open pits using excavators and requires dynamic moisture control. The extracted limestone and clay are transported directly to the factory via belt conveyor systems that extend for several kilometers. This continuous mechanical flow is one of the most characteristic features of the cement industry. These raw materials are then taken to a dome-shaped homogenization silo. Here, they are layered to balance differences in chemical composition. This mixture is prepared according to specific formulas and sent to the raw material mill. This mill can be a double-chamber ball mill or a vertical roller mill. These massive machines have the capacity to produce 100 to 500 tons of raw material flour per hour. The ground mixture becomes a fine powder smaller than 90 microns, and this powder is called raw material flour. In some older facilities, the wet grinding method is still used. In this method, raw materials are mixed with water to form a thick paste. Although it provides better control, it is now rarely used due to high energy consumption. The entire dosing and grinding process is controlled by a SCADA automation system. Flow, grinding speed, flour fineness, and gas temperatures are monitored. The ground material is sent to the heat exchange tower. Here, the material is preheated to approximately 850 degrees Celsius by moving in the opposite direction to the hot gases. The precalciner at the base of the tower separates most of the limestone and reduces energy consumption in the kiln. While these towers were previously fueled by coal, they now use recycled fuels such as household waste and used tires. These tires, separated from metal parts, burn completely at temperatures close to 1,000 degrees Celsius, providing energy. These fuels provide similar energy to coal, but have lower carbon emissions. This transformation raises the question, can the cement industry move away from being a polluter and become the foundation of sustainability? The material coming out of the pre-calciner enters a rotary kiln at a temperature of 2,700 degrees Fahrenheit, approximately 1,480 degrees Celsius. This is the most energy-intensive part of the process, but it is also where the clinker that gives cement its hardness and binding properties is formed. In this huge, slightly inclined, rotating steel tube, the mixture first partially melts and then crystallizes to form clinker. The interior of the kiln is monitored by temperature sensors and thermal cameras. The rotation speed, fuel quantity, and dwell time are optimized based on this data. However, this stage is where the highest CO2 emissions occur. The red-hot clinker is immediately transferred to a grate cooler. Here it is rapidly cooled below 100 degrees Celsius by air blown from below. This rapid cooling preserves the mineral balance of the product. The cooled clinker is taken to the mill along with gypsum and mineral additives, such as blast furnace slag or fly ash. Here it is ground again in ball mills or vertical roller mills. Each particle is continuously ground against steel balls or rollers until it becomes very fine cement powder. The fineness can reach up to 4,500 square centimeters per gram, depending on the product type. Quality is precisely controlled using automatic dosing and analysis systems. Parameters such as fineness, moisture content, mineral composition, and strength development rate are regularly tested. This transformation raises the question, can the cement industry move away from being a polluter and become the foundation of sustainability? The material coming out of the pre-calciner enters a rotary kiln at a temperature of 2,700 degrees Fahrenheit, approximately 1,480 degrees Celsius. This is the most energy-intensive part of the process, but it is also where the clinker that gives cement its hardness and binding properties is formed. In this huge, slightly inclined, rotating steel tube, the mixture first partially melts and then crystallizes to form clinker. The interior of the kiln is monitored by temperature sensors and thermal cameras. The rotation speed, fuel quantity, and dwell time are optimized based on this data. However, this stage is where the highest CO2 emissions occur. The red-hot clinker is immediately transferred to a grate cooler. Here it is rapidly cooled below 100 degrees Celsius by air blown from below. This rapid cooling preserves the mineral balance of the product. The cooled clinker is taken to the mill along with gypsum and mineral additives, such as blast furnace slag or fly ash. Here, it is ground again in ball mills or vertical roller mills. Each particle is continuously ground against steel balls or rollers until it becomes very fine cement powder. The fineness can reach up to 4,500 square centimeters per gram, depending on the product type. Quality is precisely controlled using automatic dosing and analysis systems. Parameters such as fineness, moisture content, mineral composition, and strength development rate are regularly tested. Each bag of cement is the crystallization of technology, control, and precision. This process, which may seem familiar, is actually an extremely complex system where even a small vibration or temperature difference can affect the quality of structures that will last for centuries. Thank you for joining us on this journey. Together, we've explored a material you may think you know, but have never really looked at closely: cement. It doesn't just build homes and roads. It also showcases how humanity has transformed nature through knowledge and technology. If this video has made you a little more appreciative of that quiet material under your feet, don't forget to like it and subscribe to the channel. Because behind every material in daily life, there are incredible stories where technology, humanity, and nature intersect. Cement, from the Italian word cemento, one is defined as a hydraulic binding material obtained by heating a mixture of natural limestone and clay at high temperatures and then grinding it. Although the UK's first standard specification, BS12, and the US's first ASTM specification were published in 1904. Numerous revisions have occurred over the years as requirements have tightened. In collaboration with the European Union, the European Committee for Standardization, CEN, published the EN 196 series, which includes cement testing methods. This standard defines cement standards and specifications in Europe. There are many different cement types according to European and American standards. With the recent increase in sensitivity to carbon emissions and sustainable products, blended cement types are becoming more popular. The general classification of cements according to the TS-EN 197-1 standard is defined in Table 1. CEM 1 Portland Cement CEM 2, Portland Composite Cement CEM 3, Blast Furnace Slag Cement CEM 4, Pozzolanic Cement CEM 5, Composite Cement Table 1. General cements according to the TS-EN 197-1 standard. Other cement types not covered by the TS-EN 197-1 standard but covered by European standards are defined in Table 2. TS-EN 14216. Ultra-low heat cement TS-EN 15743. Supersulfate cements TS-EN 14647. Calcium aluminate cement TS-EN 413-1. Mortar cement TS 13353. Boron activated belite cement TS 21. White Portland cement TS 1769. Sorrel cement. There are basic parameters that are tested in cement produced according to standards. Cement properties are examined through physical, chemical, mechanical, and advanced analyses. The most important of these are the compressive strength, setting time, and fineness of the cement. Compressive strength is tested by preparing a mixture with standard sand and a specific water-cement ratio in accordance with standards. The mixtures are left to cure in standard molds and under standard curing conditions. Compressive strength tests are conducted at 2 and 7 days for early strength and at 28 days for final strength. The results are expected to meet the conditions specified in the relevant standards. Setting and hardening times refer to the process of the cement paste beginning to plasticize and completely harden. The setting start and end times are measured using a VICAT device. There is no requirement regarding the setting end time in TS-EN 197-1, but the setting start time must comply with the standard. The setting start time is particularly indicative of the workability of fresh concrete. Cement fineness. There is no limit value for fineness in TS-EN 197-1. However, cement fineness is an important factor in early strength. An increase in cement fineness will increase the reaction with water, i.e., hydration. This leads to an increase in early strength. Although there is no limit value in the standard, literature studies have addressed the effects of cement fineness and particle size distribution and have shown that there is a certain limit value. The effects of cement fineness and particle size distribution have been discussed in studies. The construction and building materials industry is filled with materials that interact with us in every aspect of our lives. However, cement holds a unique place within this vast spectrum. Cement-based systems, which create a variety of products and systems, are an essential element of the construction industry. The future of the cement industry is being shaped by sustainability and innovative technologies. CHIMSA's approach is based on the goal of reducing environmental impact and creating a greener future. The use of clinker, which leads to high carbon emissions in traditional cement production, is being reduced, and a shift is being made toward alternative raw materials and low-carbon clinker technologies. Furthermore, the cement industry is taking steps to increase energy efficiency and integrate renewable energy sources. Resource use is being optimized through practices such as the circular economy and recycling of waste concrete, while emissions are being significantly reduced through carbon capture and utilization (CCUS) technologies. These innovations aim to reduce the environmental footprint of cement production and establish a sustainable production model. In this process, the cement industry is undergoing a sustainability-focused transformation, armed with technology and innovative solutions.